Welcome to tutorial 21, which is still on drill 17 single sideband. And in this tutorial, I'm going to go outside the standard syllabus because I think it's important for you to see the simplified block diagrams that we're going to be doing, and we've done them on CW transmitter, a double sideband transmitter, and we've just finished doing it on a single sideband transmitter. I think it's useful to you, even though you don't have to remember this, to see the full block diagram of a practical transceiver. So I'm going to show you that, and I'm going to come back to this diagram again later after we've done receivers, because it is a transceiver. It has both a transmitter and a receiver. And I think it'll be beneficial to you, but just remember, you only have to remember the simple block diagram that I showed to you in the last tutorial, number 20. On screen we've got the block diagram of a single sideband transceiver. You do not have to know this diagram, but I'm going to point out the parts that you should know. I'm just going to draw a line across the screen, because the top half is the transmitter and the bottom half is the receiver. And I've just drawn them off screen, so I'll redraw them so you can see them. This is the receiver, and the bottom one is the transmitter. We show a power supply connecting to all stages. Let's have a look at what we've learned so far about single sideband transmission. The layout of this diagram is a little bit different than what we did, but it's the same thing. We have a microphone that takes the audio. I'm just going to clear my screen up a little bit. We have a microphone which takes 0 to 3 kilohertz audio from the operator. So 0 to 3 kilohertz goes into the microphone, it's amplified by the microphone amplifier, and it goes into the balance modulator. Also going into the balance modulator is the carrier oscillator, which is a crystal oscillator, and it has two frequencies, 7.0015 MHz and 6.9985 MHz. Those two frequencies are so that we can select the appropriate sideband to go through the sideband filter. The sideband filter here is the crystal filter, the sideband filter shown in tutorial 20, but here we've got the schematic symbol for a sideband filter. A squirrely line at the top, squirrely line in the middle, squirrely line at the bottom, and you notice the top line and the bottom line, the high frequencies and the low frequencies, have got a stroke through them that indicates this is a bandpass filter. It only passes the middle frequencies. So the function of the filter is to select the desired sideband. The function of the balance modulator is to suppress the carrier and give us two sidebands. So at this point we have two sidebands and a suppressed carrier. At this point, after the crystal filter, we have single sideband and a suppressed carrier. I'll talk about this later, but you'll notice that the carrier oscillator is used in the receiver. The carrier oscillator is used in the receiver as the VFO, but we'll talk about that later when we do receivers. We'll find a lot of the stages in a transceiver can be used in both the transmitter and the receiver. So our sideband generation is being done for us by that stage there. All of those stages, their entire function is to generate single sideband and the sideband that we want. Now the rest of every transceiver is amplification and frequency changing. The carrier is on roughly 7 MHz, so the first IF is 7 MHz. That's just an amplifier. It has to be a linear amplifier because any amplification done after modulation with amplitude modulation must be done with linear amplifiers. So we've got a 7 MHz SSB signal here. at that point. Then we're going into a mixer, and the oscillator feeding that mixer is on 41 megahertz. So F1 plus F2, this is going to be on 21 megahertz. And it's still our single sideband signal, but it's now been amplified and frequency changed. We're going to amplify it again, so we're going to have exactly the same thing there. It's just going to be bigger. Then we go into another mixer. We're on 21 megahertz going into this mixer on our wadded sideband, and the oscillator is on 8 to 8.5 megahertz. Well, let's say it's on 8 megahertz at the moment. 8 plus 21 means we're going to have a signal coming out here on, and that looks like it might be wrong. Should be 29. That should be 20. Well, we'll just say 29 megahertz. That'll do for now. So our oscillator on 8 megahertz mixes with our wanted sideband, which has been amplified and frequency changed already, on 21 megahertz, and that's going to give us 29 megahertz there. F1 plus F2, 29 megahertz. So at this point we've got our signal on the frequency that we want to transmit on, and it's been amplified. The last thing to do is to amplify it even more. So we go into 3 stages of amplification. These are all linear amplifiers. They have to be linear amplifiers. SSB must use, AM must use linear amplification after modulation. So we've got 1, 2, 3 stages of amplification: a pre-driver, a driver, and the power amplifier, and up the transmitter. Now that's a practical block diagram of an SSB transceiver. We're going to talk about the receiver section later. We'll be talking about this much more later, because it shows you that the simplified block diagrams that we are looking at are very much like the real transceiver. This transceiver goes through different stages of frequency conversion. In our simplified block diagram, we only went through one stage of frequency conversion. This transceiver goes through a few. I'll just do this again. This is where we manufacture our single sideband signal for transmission. And this is all done at very low power levels. These 4 stages here operate in the milliwatt area. Microphone amplifier, balance modulator, along with the carrier. The balance modulator suppresses the carrier and gives us double sideband, and the crystal filter, the bandpass filter, passes one of those sidebands. Then we amplify, then we frequency convert, then we amplify, then we frequency convert, and then we amplify again, an awful lot. So we come in at 7 megahertz approximately, we mix with 14, that gives us 21, we amplify, we mix 21 with 8, and that gives us 29 megahertz on the output. And there's no more frequency change from that point on. So I think you should have a pretty good understanding of an SSB transmitter. And when you look at it, there are only amplifiers, oscillators and filters. There isn't anything else. The microphone is an audio frequency amplifier, amplifies frequencies between 0 and 3 kilohertz, that's voice frequencies. The balance modulator is a special type of mixer. The oscillator is an amplifier with positive feedback and a frequency determining device. The filter, we've not yet to discuss filters, but that doesn't do any amplification, it's just a filter stage. An amplifier, a mixer, is just a special amplifier that's non-linear, so that it mixes, so that's a non-linear amplifier. Oscillator is an amplifier with positive feedback and a frequency determining device. More amplification, more mixing, just with an amplifier which is non-linear, and an oscillator, and then 3 stages of amplification, and you've got a fairly practical SSB transmitter there for you. Now, I haven't forgotten to go through your sample exam questions. I'm going to do that now in the next tutorial. These are the sample exam questions for SSB transmission. We'll go through them, and I'm going to revisit this block diagram later on after we've discussed receivers, and hopefully you'll be able to understand the whole block diagram. There are controls on a radio. These numbers, 1, 2, 3, and so on, 6, 7, 8. These are the controls on the radio that adjust those things, and we'll talk a little bit more about that later. Alright, see you in the next tutorial. Cheers for now. This is Ron, VK2DQ.